So, hello everyone. Welcome to our week two of the software security course. So this is lecture three, like starting the introduction lecture as lecture zero. So this is lecture three, and in today's lecture we will be looking at the continuation of what we had looked in the previous lecture, the compilation process, specifically the linking and loading, and we will look into assembly instructions specifically for x86 32-bit architecture, right? So that will be the agenda of today's and tomorrow's lecture. Mostly with these two lecture and probably next week one lecture, the basics, the basics of these compilation and the binary stuff would sort of be over, and we'll be jumping directly into these security exploits, right? So a quick recap of what we had seen in the previous. Right, a quick recap of what we had seen in the previous um, week. So in the previous week, we had seen the OS, what's the importance of the operating system. So it's basically to uh, manage all the different applications which are running on a system and ensure that they don't interfere with each other, right? And the second aspect what we saw was virtual memory. So basically, whatever your main memory is being accessed, that's your working set, as in all the accesses, your memory instructions as part of your assembly code, whatever you are storing or reading from a memory, everything is from the main memory, which is the physical RAM. But since its size is limited and also since it's shared, to ease developers uh, programmability and to ease that task, right? And also for easy code development, we sort of looked into virtual memory, which sort of specifies that the whole entire address space, 2 power 32 or 2 power 64, based on 64-bit or 32-bit architecture, the entire address space, how whatever region that can be addressed, is entirely dedicated to that application. And despite the fact that your physical memory will be much smaller, significantly smaller, but the operating system is having a mapping from your virtual memory to your physical memory, and this mapping will sort of specify uh, where the actual address is being, where the actual data is being physically stored in your memory, right? That's the virtual memory concept. So and the final uh, aspect what we looked in the previous week was how does a program get compiled into a binary. So the compile, that term itself is sort of not a correct term, because if you take the whole pipeline, compilation is sort of one stage in that complete pipeline. So there are multiple stages, starting with the pre-processing phase, and then the compilation phase, which sort of converts it into assembly instructions, which human readable assembly instructions. And then we have the assembly stage, which converts it into object files, which is mission code. Mission code. And finally we have finally we have the linking stage, which sort of links the application, right? Links all the libraries, all the dependencies, and generates the final executable. So this is what is the whole the program to binary pipeline, and this we had a previous a brief look into, and also we used various parameters passed to GCC hyphen C hyphen S hyphen E hyphen P. So various flags we passed to GCC and saw the output of all these intermediate stages. So one aspect that we are still yet to fully look into is the linking stage specifically. So in today's lecture, we will be looking at the linking stage, uh, the different types of linking, and what happens in each linking type, right? So before going to that, so L format, so basically in Linux operating system, the binary whatever we sort of obtain after the whole compilation and the linking stage, right? So it follows something called as the ELF format, which is executable and linker. So this like a specific format, and basically what this format is sort of denotes is it denotes. So if you take an executable, it will not only just contain your code, it will contain data as well, and it will contain some other debugging information, right, and some other metadata, all those things. So basically this L format sort of specifies the exact layout where this code section would be present, where this data would be present, all these things your sort of the L format decides. Like that's the overview of the L format. So we won't be going into the details of the L format currently, right, but so basically the overview is in Linux applications, this the format that the final binary that gets emitted would be following. So it's sort of like a template. So in the first part there will be your code, second there will be data and some information and all those stuff, right? So for example, if we take an take a code and for example hello world dot c, right? So if I just run hello world dot c, it just prints hello world. That's the entire application. And if I look at the file type of a dot out, it specifies that's an ELF file over here. So basically it follows the ELF format, and there are tools which sort of reads this specific file. So similar to how you have a .mp3 files, right, or mp4 for video applications, it sort of follows a format. Similarly, a binary executable sort of usually follows this ELF format. And there are tools, utility tools. For example, there is a tool called readelf. So it basically reads this a.out file, the elf file, and you can get various information out of this elf file. So for example, if I do readelf, you have like so many options. And so basically why I'm going through this utility tools is later when you look at these security exploits, usually you won't be looking at the source code directly. You will be given a binary executable, and you should basically try to look at the assembly instructions and sort of read the ELF file, use these tools to find an exploit and make that exploit, uh, make that vulnerability into an exploit basically, right? And gain control of the application. So at that time, using these tools would be quite useful, getting to know these tools. So for example, over here there is this -a option. Okay, so readelf -a dot out. So basically -a option is sort of, it specifies what all uh, uh, data is present as part of the self file. So if you notice the ELF format, right? So it contains various metadata apart from your actual code and data. So the entire hello world application is just like sort over here, right? Cat hello world.c is just like 4 lines, but the L format sort of has to so there is like a header, as in the basic information of this L file a dot out, and if you notice, it specifies what's the entry point address of the executable, what version I am, what the mission, and what's the ABI version. So ABI will look later, and what are the different sections. So sections as in you will have different parts within your final executable. So your final executable will sort of be split into multiple parts. So if we sort of look into um, so if we sort of take a process, right? So this is your executable, means when you run this executable, when you execute this binary, right, when you run this executable in your memory, so say this is like higher memory address and this is the lower address, assume, right? So you will have your data section over here, your code would be present over here, and followed by that your heap and your stack. Okay, so your stack sort of grows downwards, starting from the higher address to lower address, and your heap sort of grows upwards. So this part of stack, what happens internally, we will look in tomorrow's lecture. But for now, this is your general process layout. So when your binary is executing as a process, right? This is the layout in your virtual memory. Process layout in virtual memory basically. And so this data and code, right, each thing is actually a section in ELF. So we call it as sections or segments basically. So um, so this will be your code segment, this will be your data segment, this is stack segment and a heap segment. So your ELF format sort of has information with respect to where each section sort of starts and ends in this entire virtual memory. Okay, and so that's what we have, this start of section headers, size of headers and all those stuff, right? So all this information is sort of present in a top level header file at the start itself of the self file, and followed by that you will have all this sort of the actual information, the actual binary, your code, data segment, and all those things. And if you look at this specifically, the entry point address 1090. So basically, if I do an object dump, right? So these commands we have discussed in the previous lecture. So if we look at the object dump of a dot out, and if we look at sorry, not this. So if you look at the main function within the dump file, so basically I transform from the machine encoded instructions into uh, human understandable assembly instructions, right? So if I do the object dump, right? So basically your entry point address. So from where will execution start when I execute this program? So dot slash a dot out, right? It prints hello world. So usually in your general 101 introduction to computer science or introduction to C language, you will generally be mentioned this is your the main function is the starting, right? But usually the main function is not the actual start, as in it does so your application starts from main function, but there are sort of other internal functions added automatically when you compile your application. um, and one such function is known as this underscore start function, and this is where your application actually your process starts the execution. And if you look into this start function, right? You have this call instruction basically, right? So this call instruction, if you notice, there is this main keyword over here, right? So it is specifically this call instruction denotes that the control jumps from this underscore start to the main function, right? So all this information is sort of present in your ELF file, right? And together this the ELF format, okay? And so till now we have looked at properly at all this up till the assembly stage, but what happens in the linking stage, we just had a quick look only. It's important to understand fully what linking does specifically and what are the different types of linking, okay? So basically when we take a normal program like subl, for example, um, take a program main.c, right? So we have let me close these things. Okay, so basically you have this main dot c over here. It's somewhat similar to the one which we um, studied, which we went through in the previous lecture, except that it has two extra invocations, one to function one, fun1, and fun2. Okay, and if you notice in the main.c, you don't have the definition for fun1 and fun2, right? It's not there in the same source file. And now if you try to compile main.c, and if you it will basically return an error, right? And this error is, if you notice, it denotes undefined reference to fun1, undefined reference to fun2. So basically it was not able to find um, the code where this fun1 and fun2 is located, right? And this error, right, this error over here, this error is basically uh, emitted by your linker. So if you notice this, right, slash user bin slash ld, so it is basically your linker is trying to find whether some functions are there, fun1 and fun2, and it sort of sees that the code is not there and it throws an error, right? So uh, uh, so we sort of, what we do is, now if we compile along with main, right, all this, then it sort of uh, the compilation passes and even the linking passes, right? And now if we execute it, executes. So basically it invokes function 1 and function 2, and it prints these messages, right? So this is what, like, it happens in linking. So for now let's sort of take out these invocations fun1 and fun2 from the main, and just have this printf statements alone, right? Just one printf statement would be enough, okay? And we have this main. So basically now if I just so it just in function main1, so that's the message. So in this in this program we will see what happens during the linking stage basically, right? So if I to understand better this linking stage, right, first we should start from the assembly pipeline, as in, just if I use this hyphen c flag and look at the main.o, which was emitted after I executed this command, right? So main.o is ELF file. Let me use the hyphen m32 bit architecture, right? So it's an ELF 32-bit file, and it's an int for Intel machines, right? Now if I look at the object dump, if I look at the main object dump, just that main.o file, right? And specifically if I look at um, the call instruction within main. Okay, so let me use the debugging flag so that it's sort of easier for you to notice, right? So over here, so we have this printf function. So I use the object dump -s flag. So basically it makes use of the debugging information. So when I use -g option, you enable the debugging information to be inserted. Basically it sort of adds some extra data as part of your ELF file, and all this data will sort of enable you to uh, do the debugging in a easier way. So it will contain your source code. Also it will contain like this single line of source code got translated into these set of assembly instructions. So this mapping, everything will sort of be retained in the final binary also. But usually when you uh, deploy any application, you will be removing this debugging information, because adding this debugging information will increase your code size and slow down your application. And uh, so for better performance, usually this -g flag and this debugging information won't be enabled, but here for debugging purposes we are using this -g flag. And in real world situations, when you have a binary and if you want to find an exploit, it will usually be the case that you won't have this extra debugging information, as in you won't have this sort of privilege where we have the source code uh, and also your assembly instructions mapped together, so that you can easily understand what your function, your code does, right? This privilege you won't get in real world situations, right? So coming back to this linking, right, we sort of compiled your main.c into an object file, like a standalone object file, right? We have not yet gotten to the linking phase. We have just reached the assembly phase. That's the translated into an object file. Now, if you notice your printf function, so basically there should be a call instruction, and it should be sort of like call printf or something. But if you notice, it's sort of calling some line number, and that line number is within the main function. Line number 53 is within the main function itself. And if you try to execute this main.o, right, it will fail. Um, so it will basically fail. And if you notice the memory address where it's supposed to start over here, the entry point address, when I try to read the ELF file with respect to main.o, the entry point address is 0x0, right? It doesn't make sense. If I notice what's present at 0, it's the start of the dummy function, and I'm for sure know that execution should start at the main function only. So it means that it's not like a proper standalone executable. There is still some work to be done. Specifically, this printf function over here, right? This call should actually go to the printf function, but it's landing somewhere over here within your main function, which is wrong, right? And now if I look at the final executable, so if I just do gcc main.c, and if I do -m32, right, and if I look at the final executable, so this is where I have done my linking also. So linking is sort of happens implicitly, and if I look at the dump of the linked executable, right? So this is your main function, and now the same. So if I have this side by side over here, so side by side, if I have this, right? If you notice specifically this line, and this line. Which one? Yeah, this one, right? So side by side I'm having it. So here in the printf function, this is set of instructions from 46 to 58 sort of got translated the assembly version, and in the right hand side it's like 1213 to 1227. So these are the set of instructions specifically in that line number 51 in the left file and line number 223, right, the highlighted ones. If you notice in the left side it's the object file where the linking has not happened, and if you notice the call instruction, it is pointing somewhere within my main function. But if you notice in the right side, there are two differences. One, the call instruction is sort of now complete, as in if you notice it is denoting call space puts at plt. So basically it is the printf function, the puts function it's invoking, and it's specifying the address where the puts function is present. So basically this is the address, so 1070. If you search for 1070 colon, this is the puts function where it is present, right? So this sort of this is the whole process of linking in a nutshell, right? uh, uh, so basically all your functions, your library functions or anything, these dependencies, whatever is not part of your source code, the linker sort of finds where these dependencies are and uh, completes your executable, right, sort of fills in the blanks. So it sort of replaces this 53 call 53 in the left side and replaces that with call 1070, specifying exactly where the puts function is located. And this is the role of the linker in the whole uh, program to binary pipeline, right? And so basically the linker sort of, you won't be having all your source code in the same file. It can be split over multiple files, or you can be using different third party libraries, right? So your one of the usual library would be your glibc library. So all this stdio.h, right, your printf, scanf, all these things, right, all these functions, the code is actually present in a library called glibc. And this library is sort of a dependency, and if you want to use any library or anything, right, this should sort of get linked to your application, linked to your the sort of link to main.c, and this is what happens. So in the linker stage, what happens is the call to printf, right, it's sort of fixed. So that's what happens in the linker stage. Basically this call over here, it denotes 53, whereas here it denotes the proper address where my printf function is located. And just to go a bit deeper, right, you can look at the elf file and use a command readelf -- relocation main.o. So basically what this denotes is over here, right? So in your elf file, okay, so main.o is also an elf file, the object file, that's also following an elf format. Your final executable is also following the elf format, okay, and within that there is a section within your elf file, and that section is known as relocation information. Basically it sort of contains information, this highlighted information sort of has this information which tells all the pending instructions that has to be fixed in order for it to be executed properly. So for example, if you notice over here this specific line, okay, this specific line mentions we have to find a symbol called puts, that is printf function. So basically, like if I just pass a string to the printf function without any other integer or something to be printed like percentage %d, something like that, just a string if I'm passing, the compiler usually converts that printf into a putS function. Okay, so that just for your info. So it's basically the same putS and printf of a string, and this highlighted line specifically mentions in my main.o file, it mentions at offset 53, okay, starting from the 0 location in the elf file, at offset 53 there is instruction which sort of has to fill in where this putS function is present, and this information is sort of passed to my linker, right? So when I execute this command gcc main.c, this happens internally. So from main.o, okay, this information, all this information is passed on to my linker, and my linker looks at, okay, at line 53 there is a reference to putS, okay, but this reference is sort of incomplete. So this reference is sort of incomplete. So if you notice at line 53, so call 53 is mentioned, right? So at line offset 53, there is a symbol putS, but it's sort of incomplete, and the linker has to find where the putS is located. So this is what my elf file will sort of store along with all this information, right? My code and data, this global variables and read only section and all those things. These relocation symbols, basically all this extra information that has to be filled in for the binary to be executed. All this information is also part of your elf file, and all this is stored in a separate part within your file, which is known as the relocation section. Okay, and now if you look at, if I use the same command, so this basically this main.o is sort of an elf file, and if you notice over here it is not mentioned relocatable. Okay, and now if I do the same on a.out, that is after linking. Okay, if you notice it is not mentioned, it is relocatable, and if I use the same command readelf hyphen rel uh, relocations a.out, sorry, a.out, if you notice over here there is no this specific section, right? So there is no that line offset 53 symbol putS, it should be found. So that information is sort of removed from my relocation section. Okay, and this basically signifies that in the final executable, this specific line 53 over here, right, this line 52 call 53, is the linker sort of uses that relocation entry and finds where the putS function is, and at linking step it knows where my glibc library is present. So the linker is sort of like an extra artifact link, part of your compiler, and it sort of links your glibc application. Okay, it copies the glibc code and everything and maps it into the process virtual memory. So if you notice, I mentioned this is how your process layout looks like in the virtual memory. Okay, so specifically your code and everything, right? So as part of this code section, even your glibc would be linked into, okay, the extra library whatever I'm using, this glibc having printf and scanf, the extra library will also be linked into your application, and the final that's this is how the binary will look like. And once it is linked into, my linker will sort of know where the putS is available, and it sort of fills in the application, fills in the instruction with the appropriate offset. And the left line over here, this left column 121c 121d, is basically like sort of offsets starting from 0, the start of the binary file. At offset 121c, this specific instruction is located. So this is what it denotes. Okay, and now when I execute dot slash a.out, it executes properly. Okay, now so any doubts till here, the basic function of linking? Okay, so I mentioned that whatever code you are using, right? Um, I mentioned that whatever code you are using in your process, your glibc code, the printf and scanf, which are defined in your library, right, is glibc library. These will be linked into your main.c, the final binary. So currently you will just be having your main function, but along with this you will be having copies of printf, scanf, and all those things. Okay, and so basically this printf logic, scanf logic, everything will be copied into the code segment of the elf binary. Okay, so this is what basically your linker would perform. Okay, but there is so disadvantage, as in there are generally two types of linking. So first we will look at static linking. Okay, so static linking is, as we discussed here, right? All the code, even the logic of printf and scanf, everything will be sort of loaded as part of your executable, and it will be present in your code section. Okay. For example, if you notice over here, so for to generate a static link executable, right, I should pass this extra flag called hyphen static. And if you look at the a.out, if you notice it is mentioned elf 32-bit executable statically linked. And if you look at the object dump, okay, of your a.out, so if you have this putters function over here, okay, so um, your main function, so this is your main function, and if you notice over here this specific line, right, so this is the line where I'm calling the actual printf function. If you notice, you have this information called io underscore putters, and if you go to this function, you have the entire logic. Okay, you have the entire logic of this printf function. So basically it will print to your screen whatever message you execute. Okay, and if you look at the size of the executable, the a.out file, it's around like 700 kb, and this what is basically static linking. So all the dependencies, everything, a copy of that is made into your application, into your binary, and all that code is present as part of your binary itself. And now when you sort of want to execute the binary dot slash a.out, it executes properly, and once you sort of finish this static linking stage, right, when you execute dot slash a dot out, this statically linked binary dot slash a dot out, what happens behind the scene is you sort of first invoke the operating system, and this operating system, what it will do is it will set up a virtual memory. It will set up a virtual memory, and this a.out statically linked executable I mentioned, right, it has a code section, it has a data section, it will have a stack and all these things, right. So all these sections will be mapped to your virtual memory, as in it will be a virtual memory will be sort of generated. It will start a process, it will start a process at the offset. uh, sorry, right. So basically the operating system will start a process and it will give a process ID, right? And what it will do is it will create some memory. It will create a virtual memory and map these segments, all these code and data segments into the virtual memory. Okay, and after doing this, it will pass the control to ampersand underscore start function. So I know I mentioned right in the readelf hyphen h over here. So readelf hyphen h a dot out. This entry point address, right? So this basically your address where your underscore start function would be present. This underscore start, and once your operating system has finished creating the virtual memory and loaded everything into the memory, all this executable and everything, after the mapping has done, it passes control to underscore start function specified in that entry point address. And once it passes control, this sort of continuous execution from underscore start, it will call the main function, and from that it will call the adult functions. The logic will continue. So basically, loading is sort of um, loads your binary which is present in your disk. It starts a process, attaches a process with that binary, and loads all the code and data, everything into your memory. Gives it an address for you to refer to, for the instructions to refer to and execute. And once that loading has done into the memory, it passes the control to my executable starting at this underscore start function. So this is what happens in loading a statically linked executable. Okay, and if you have to look at the runtime view of a process, okay, so what I can do is I'm just inserting a infinite for loop at the end so that it keeps on running continuously. Okay, so what I can do is I'll execute the same program. Okay, and now so since it's a for loop, infinite for loop, it will keep on executing. Okay, and now what I will do is I will use command line tool like top. It's not required. So basically, to find a process ID of what this a.out process is, right? So I have various applications over here, and basically a.out is the command, right? Dot slash a.out, and the process ID attached to this command is 133724. I copy this ID, and what I do is I use this command slash cat command, display command, and I display a file called slash proc slash 133724 maps. So basically, this 133724 is the process ID that of this a.out executable, the process which is attached to this binary file. Okay, and I look at this file specifically slash proc that specific process ID slash maps, and if you look at this file over here, if you look at the output over here, right, it basically denotes the various segments present in your code, present in your process, basically like the runtime view of the process. Okay, and how to read this? So basically this slash proc, okay, this slash proc is sort of a folder which will contain information with all your running processes, okay, active processes. So if you just go to cd slash proc and do ls, right? So basically all these numbers over here denotes different processes. Okay, and specifically my process id a.out is 133724, and there's a corresponding folder to it. And if you notice over here, there will be like sort of different files attached to this process. So this is all like OS managed, and specifically what I'm interested is in the maps file. So basically this maps file will contain so I mentioned over here, right, my code and data stack, everything, my operating system loads into the virtual memory, maps it to a virtual memory. So this maps in file will contain where all these code and data stack and everything has been loaded into the virtual memory, specifically at what address range, okay, and how to read the output of this maps file is this left column over here, right, starting over here, 08048 4 zeros over here. And similarly, this first column denotes the start and end of the address range, okay. And this column over here, this VDSO stack and heap, okay, these denote the segment name. So if you notice, I have my heap segment, and this is address range. It starts from 899 F 000 and ends at 89C1 000. And my stack location, if you notice, it's at like a higher address range. Okay, so if we look at this diagram over here, I have mentioned higher address range to lower address range, and my stack is sort of at the top. Okay, and if you look at the terminal, it's sort of the output of the map file. My OS has placed the stack at the top actually. So it starts at FFCB this address and ends at this address. Okay, and all these this region over here specifically, there is no name given to this region, but this region over here, this is your code section. Okay, so it 8049000. So if you look at the object dump file, um, your object dump, right, 80, what address did we look into, right. Okay, so basically if you look at this is the start of your code segment. Okay, and so like that, every information, code and data, your heap and stack, where the absolute virtual memory address where it is located is present in this maps file. Okay, and to be more concrete, right, let us look at another example. So let us look at this example called main underscore 2.c. If you look at this main underscore 2.c file, it basically has two variables a and b, and another variable which is a pointer to integer. I allocate using malloc, a dynamically allocated region, size of int. Okay, and what I do next is I enter two numbers a and b, and I invoke a sum function, and I pass a, b, and this c pointer. And basically this star c, this c pointer, wherever it's pointing to, that has the sum of all these three numbers, which is a plus b plus glb, and this glb is a global variable over here. Okay, and finally what I do, I print the sum of all these numbers, which is placed at this address star c. I dereference the pointer, and also along with it I uh, print all these extra information, which basically prints the address of A where it is present, address of B, address of C, and what memory location C points to, like what's the value C contains, and the address of GLB. Okay, and now if I sort of execute, okay, and so if I look at the top, so here it denotes enter two numbers. So I enter 22 and 22, and this is the output, sum equal to 99, and I get these addresses, right? And now if I look at what the process ID, if I look at the map file, so a dot out process ID is this, I copy this and I look at the maps file, cat proc, okay. So specifically if I look at this over here, okay, so address of A, so my variable A, the first number 22 is present at this location address FF9 EA30C. If I search where this address is present, right, this FF3A90C is present in my FF9EA, okay, FF9EA is present within this address range, okay, and this address range is known as the stack address range. So basically this, like all your local variables and everything within a function will be stored in the stack, right? So in the same way, this is what the address where my variable A, variable B is present is actually the stack region, which my operating system has allocated to this process. And if you notice where the address of GLB variable, the data, the global data variable is present, it's a 8102. So if you notice 8102, it's over here. Okay, so this is the address range. Okay, and address of C. So basically, where the C variable is stored, that's stored on the stack. So if you notice over here, I am declaring a pointer, okay, in star C, and this star C, this C variable is on the stack, but the content what this C is actually evaluating to, what this variable C is actually having, is an address location which is pointing into a heap location, which I use the malloc function and I allocate on the heap. And the value of star C is this specific variable, this specific value 929 33E0. And if I look at the address where that is present, which segment, it is present in my heap segment. So basically the value what the variable C is pointing to is within your heap segment. Okay, so this is sort of like the reason why I showed this example is all the variables, right, whatever you are using, the local variables or global, the heap variables, they are sort of not like contiguous in the next to each other, but depending on where you are using it. If it's a local variable, it is stored in the stack, and your stack segment is present separately. And if you are dynamically allocating some memory, that will be in your heap segment, and that address range is separate from your stack. And if you are using some global variables or something, that is present separately in this segment over here. So the operating system sort of maps different sections of your binary, each serving a different purpose, into different address ranges within your virtual memory of that process. Okay, and another important thing from this maps file that you should notice is the second column. Okay, over here, R hyphen hyphen P, R hyphen hyphen XP, RW hyphen P. So basically what this denotes is, leave out this P notation, this first three letters within this word R, W and X. So it basically denotes whether the address range can be read, it can be written, whether I can write into that address range or whether I can execute in that address range. So if you notice over here, my stack address range and my heap address range, it is denoted as RW. That is, I can read from the stack or write into the stack, or read from the heap and write into the heap, but I cannot execute anything. So basically, I cannot store any code as part of my heap or stack. Okay, and if you notice specifically over here, this region, so this is my only region where it is denoted as read and execute, as in R-X. So basically I cannot write into this section. If you notice the hyphen symbol in between R and X, right, it denotes the write is disabled. So basically in my code, once it is sort of compiled, I cannot change my code section. The logic stays as it is. I cannot change the code section. I can just read from it and execute the instructions. That's it. So this policy over here, right, whether it can be read or executed, or it can be read and returned, all this will sort of be um, managed by your operating system. So this section, so basically your operating system maps the stack, your heap and everything into different segments in your virtual memory, and also configures whether it can be read or written or executes, and what this permission will be, where it will be used is when you try to access your memory, right, as part of your hardware, these permissions will be sort of checked. So if I try to um, read, or if I try to change my code segment or something, okay, say if I have a um, so over here, right, say if I have like a in star p, and I do like p equal to 0x800 d0 something like okay, something like this, as in like the variable p stores this address, and if I now try to access this address and write some garbage data, this my OS, my hardware will stop, because this address over here 8049 something was mapped to this code segment, and it does not have the write permission enabled. Okay, and because of this my program will stop, and it will say some page fault error or some memory access error. Okay, so this is usually this is what usually happens in the linking step, so linking and loading. So first it finds out where the putters function is all present. It sort of links that code into your application, and then you have the loading taken place, where the operating system sort of loads the process, the binary, creates a process, attaches the binary to that process, loads all the stack and heap everything into, maps it to the virtual memory, gives it an address for you to refer to, for the instructions to refer to, and also configures these permissions, whether it can be read and executed, or whether it can be read and returned to, all these things, and passes control to the starting point of the application underscore start function, and it resumes execution from there. So this is what happens in your linking, static linking, and loading a statically linked executable. Okay, and the process layout, as we discussed, this will have your stack at the start, your heap, your code, and data, and in between there will be like some other information which is sort of else specific, or something which is to be done at runtime. Okay, so this is what your process layout would be, would look like. But there is a disadvantage with the way how we currently link. So currently we sort of looked at static linking, where we mentioned if I'm using like printf function, the logic of this printf function copied into the executable code section. Okay, and say if I'm having and like the size of my entire executable was around 700 KB. Okay, and usually what happens is um, uh, the if I'm using, say like here I'm just using printf, but say I'm using like printf, scanf, file read, file write, like that, like say 200 functions. The glibc library has network functions. You have lots of functionalities, right? So say you're using like 200 external defined functions, not only glibc, some other library also you're linking along with your main.c application. Okay. Now what will happen is all this 200 functions, logic and code will be copied into your executable, and the size of your executable will be not in KBs but will be in MBs. And what this will hamper is it will increase your code size drastically. So to avoid all these things, right, what we sort of do is we sort of and also another issue is uh, if I have say three different processes, okay, say I have so, right. So say if I have main, say if I have main 1.c, I have main 2.c, okay, and both are using printf function, right, printf or putters, okay, and both of them are separate standalone executables, and I want to create using statically linked executable, right. So what will happen is copy of this printf function will be separately stored in main1.c, copy of again the same printf logic within your glibc library would be stored in main2.c also. So basically the same code functionality will be sort of copied into different executables, but the same logic, same code snippet only, but it will be copied twice. They are different executables, but the information within this executable is sort of redundant, and your system will have like this so many applications, and printf logic is sort of very commonly used, and almost all applications will be using printf logic. In that case all your applications, right, will be having the logic of printf in the code section, and this is what this leads to is wastage of memory, right, because now all this will be stored on your secondary disk. If I want to execute all this code as part of the all this code simultaneously, when I want to execute dot slash main 1 dot slash main 2 like that, your printf function will be present in memory separately for each of these executables, even though the logic is same. So this leads to memory wastage. So for that what is usually done is we treat this as sort of like a shared library. Okay, so we treat glibc as a shared library, as in your main one, your all your applications main to whatever is using glibc, they won't be copying the entire copy of glibc or the printf or putters function logic separately into the code section. Instead what they will do is they will just have like a they will have like a sort of indirection, as in instead of directly invoking call printf, right, what they will do is they will invoke call printf at glibc, or so specifically, to be specific, right, they will have call printf at plt or something. Okay, so this plt will look into later, but so it will be something like this call printf at plt, and over here also it will be call printf at plt. Okay, and like this in all your applications, your printf function would be sort of printf at plt, it will be present, and the logic of this printf function will not be copied into the code section of your main one executable or main two executable. But then how will my code properly execute in my statically linked executable? my printf function was present over here. So if I look at this main function, oops, yeah. So if I look at this main function over here, there will be a printf. Okay, so basically it is io underscore puts, right? So this is the puts function, and this is the logic of the puts function. But now I am telling my final executable over here. Okay, so let me give show the with an example itself, right? So if I take main.c, this example, just printing a message, right? If I take this main.c, and I'm not passing this flag hyphen static, whereas instead I'm just passing main.c hyphen m32 and hyphen g. Okay, and first difference, right? If I look at the a.out file, it shows it's called dynamically linked and not statically linked, and there is some extra information over here called as the interpreter. We'll look into this interpreter shortly. If you first we look at the object dump file, a.out. If you look at the object dump file of the main function, okay, if you notice my printf function over here, my actual puts function had a name called io underscore puts. Okay, but over here if you notice there is something different. It is not invoking io puts directly, but it is invoking a function called puts at plt, right? And if you go and look at this logic wherever it is located, puts at plt, there is a small snippet given over here. So no need to go into the internals of what it does, but basically this is what it denotes, puts at PLT. This is what the logic of puts function is present in this dynamic linked executable, which is not statically linked, right? But what happens in this puts PLT? What is this functionality? Where will I get the logic of the print? Hello, am I audible? Can anyone confirm I'm audible? Was I muted like for the past few minutes? Okay. So till which part did you listen actually? Till which section like did you listen? Can anyone confirm? Because I saw the mute sign, so I guess I was muted for some time. Can anyone confirm like till which section do you like which part you listen? Till this puts function, was it audible? This puts at PLT, this stuff, whatever I was explaining till now. Okay, thank you. Right. So basically, we sort of saw what are the disadvantages of statically linking, that is copying all the code into my code section, because it will have multiple copies of printf. That's a total wastage. And if we look at the other type of linking to alleviate all these disadvantages, that's called dynamic linking, where it tells that instead of sharing copying glibc code base all this printf function into my code base of the main1 or main2 executable, I won't copy it. Instead, it will be sort of shared in some specific memory location, and main1 and main2 sort of has to go and invoke the functions at that specific location. So basically, there will be just a single copy of printf, uh, that logic in your physical memory. Physically, it will be like a single copy, okay, and the different executables should sort of have to go and see where it is actually present and invoke those functions, okay. But how does main1 and main2 different executables know where the printf function is located? So if you notice in the statically linked executable, we sort of knew where the putters function is there, printf function, and it was the instruction was also like call io underscore putters. It's the actual logic where the putters function is present. But if you notice over here in the dynamically linked function, it's the instruction is like call putters at plt, and this is the complete logic of putters, which doesn't make sense, right? So what usually happens is at runtime there is in dynamically linking, right, when this code is not fully copied, right, it's like sort of shared between executables. What usually happens is there is a extra component linked along with your application. So along with your application there is a component called as the so along with your application there is a component called as, so along with your main1 and main2 there is a component called as the interpreter, right, which is sort of linked along with your application, okay. And this is sort of contains code and data, okay. And this interpreter, what it usually does is at runtime when I do dot slash a dot out, right, and when I come across the function printf, okay, you notice this you have this instruction called call putters at plt. So basically this call putters at plt transfers control to this interpreter, okay, and this interpreter sort of contains a internal table which will sort of have information where my glibc functions, all these library functions, printf and all these things are present actually in the code. So where it is being present, that common area where we mentioned, right, the code would be present, that specific location my interpreter will find at runtime, okay, and it will fill up the table with this address. So say if it's found at address 880, so that address it will fill up, and each time if I want to sort of go and find the if I want to execute the putters function, it sort of calls this putters at plt, which sort of goes into this interpreter like for quite a few times and looks up the table and finds it's present at 80 address and goes to 80 address, executes the actual printf function logic and returns back. And there is like an extra overhead, because now instead of directly going to the printf function, you go through this interpreter which sort of is linked along with your application, and also has to find out at runtime itself. When you do run the process at runtime, it sort of executes in between and finds out where my actual function logic is located. So this adds to the runtime overhead, but there are advantages because your memory is sort of saved, right, because now you don't have to store multiple copies of the same printf function in each executable. Instead it is sort of shared, and your interpreter, which is sort of the common piece, right, this is sort of provided by the operating system or the compiler pipeline, mostly the operating system, right, So this interpreter is automatically part of your application, and your interpreter is tasked with the job of finding where the actual logic is present in the memory. So the loading step, right, dynamic linking and loading usually happens in this way. So it sort of first finds out where the putters function is present and all those stuff, and replaces that with this putters at PLT in this dynamic linking, and at runtime still a part of linking is left because the actual place where the printf function is there is still yet to be found, and that the interpreter at runtime will find out and populate this table and all this information, and the actual code logic can be executed. So this is what happens in a dynamic linking, and this is what the OS or the interpreter does when you execute a dynamically linked application. Okay, and if you notice now what the file type of ADOUT, you notice it's an ELF32-bit. These are all trivial, but specifically over here, right, dynamically linked application, and you have this extra field called interpreter slash lib ld linux.so.2. So basically I mentioned you have this interpreter code that is linked as part of your application, right, which is tasked with the job of finding where my actual printf is located. So the name of that interpreter, which I will be using, which the process will be using at runtime to find these dependent library, that code regions and everything, is this specific interpreter called libldlinux.so.2. Okay, and if you look at that specific file, libldlinux.so.2, that is a symbolic link. Okay, right. So if you notice over here, it is if you this basically this ldlinux.so.2 is like a synonym to this specific file, and if you notice the file type of that specific file, right, i386 linux gnu, that is also an ELF file, and if you notice it is known as a shared object because it's sort of shared between all the processes. Okay, and it is dynamically linked, and you have all other information. Okay, so this is what happens in a dynamically linked application, and okay, and basically the internals of how this dynamically linked application is mapped to different regions of the memory is wait, okay, let me do it over here. Okay, so you might ask the question like how is this like shared, because in the virtual memory aspect you will be having if you are say having main underscore 1 and main underscore 2, right, and you will be having this specific like the entire virtual memory according to that process is fully with that process, right, this 2 power 32 bits, assuming it's 32-bit architecture, it's like 2 power 32 bits of bytes of address range is fully for that single application. But in virtual memory we mentioned that this entire virtual memory will be sort of mapped to a physical memory, and this physical memory will be having just like say 1 TB or 16 GB, whereas this 2 power 32 will be having like extra space. So your physical memory will be like not 1 TB, right? Your RAM is actually like 16 GB itself is sort of huge actually, 64 GB or that's it. Like if it's 16 GB, whereas your 2 power 32 is way more than that, or 2 power 64. So your virtual memory is mapped, and this mapping is all maintained by your operating system. And now where this shared library would be present is basically what we do is the shared library. I won't be copying the code as part of, so say my main function is present and all the application, right? Your sum function and everything is present in the code region. The printf function, everything would not be copied into my code region. Instead, what the operating system will do is it will sort of create a virtual memory to physical memory mapping, right? Stating that you don't like physically copy the shared library into your uh, it don't make a copy explicitly. Instead, it will just mention, it will just like sort of allocate virtually some part of your virtual memory, saying this is where my shared library is present, and it will map this part of, say this is like 0x1000 virtual memory address means, and my actual shared library, say it is at present at some address, the actual physical address on your physical device is say 0x100. So my operating system will denote this 1000 0x1000 address is mapped to 100. So whenever I try to load or store something with this virtual address 1000 from main1 executable, it will load and store from this address 0x100. So if I try to access the shared library printf or anything, it will basically access from the shared region 0x100 where the actual printf library is located. Okay, but this section over here won't contain the actual code actually, right? It will just, the OS will sort of contain the mappings between 1000 to 100. It will sort of contain valid mappings, but it won't be having the actual content, won't be stored. This will be sort of empty. So this will be sort of empty. Just the operating system will have like a mapping saying that my shared library, assume it to be present over here at 1000 address in virtual memory, it's mapped to 100 physical address. Similarly, in main underscore 2, what will happen is it will say my shared library, all this printf and everything is present at 0x2000 virtual memory address. Okay, so it's sort of like empty, but my operating system will sort of have a indication stating that assume this is the address where my shared library is present, and whenever I try to access 2000 from this main underscore 2 executable, it will also map to this address in physical memory, which is 100 0x100. So basically main 1 and main 2, whenever it's accessing 1000 or 2000, it is accessing the same address 0x100 only. And so basically that's the location where my shared library is present. So in, to put it across, right, my shared library is just present at a single location. It is not present at different locations. Okay, it's like they are not like duplicate copies, just a single copy is present, and we sort of have like different virtual memory to physical memory mappings, and my operating system also makes sure like the virtual memory is sort of separate, right? So these are like OS internals. So basically the point, the key takeaway is I just have a single copy of my shared library and not multiple copies. But if you say, if you have static linking, right? Say if it was a statically linked executable, the same thing, how it would look like is you will have your main underscore 1 and main underscore 2. Okay, it will be having sum for main function and then your printf. Okay, and say this is your physical memory. Okay, so this is your, say, printf, it is there at 0x1000 means this will be present at physical address 0x100. Okay, and similarly for main underscore 2, you will have a printf function, again some main, some other functions, and this printf function, say it is present at 0x 2000. So this 0x1000 and 2000 all different address spaces. Okay, it can be 0x1000 also, this printf. So basically this entire region is separate, and this entire region is separate. Main 1 is separate, main 2 is separate. Okay, and say this is also 0x1000 means this will be present in physical memory 0x200. So basically I am having two copies of the printf function stored on the physical device separately, duplicate copies. This is what I mean by memory wastage. But whereas in dynamic linking, I just have different mappings, duplicate mappings alone, which my OS maintains. Okay, those mappings will take small space only, but physically, my shared library is just present at address 100, just single copy. So this is what is the difference between statically linked and dynamically linked executable, right? And the loading in a statically linked executable, if you notice, uh, you won't have this extra um, information when you look at file a.out, right? Uh, Here it would have mentioned interpreter, and here you would have mentioned it's mentioned statically linked, and you don't have a interpreter along with it. So it basically means that you don't have this interpreter linked along with the application. So all that finding of taking extra steps to find out where the shared memory is located, all that stuff is sort of not required because it's statically linked, and that's why you don't have the interpreter information available in these statically linked executable. Okay, and another important aspect is the difference between this specific information not script and the script. Okay, so basically there is this command called script. So if you notice the file a.out over here, currently take the statically linked executable, right? If you notice, it is mentioned not script. So what this basically means is, if I look at the object dump file of a.out, okay, there will you can find a symbol called as the main function, and there will be this int main and all these things, right? Whereas now if I use the command called script a.out, okay, and now if I see a.out, it is mentioned script over here, elf file but script. And now let's look at the object dump of this elf file. Okay, and if we look at this, okay, so let's search for main function. So if I search for main function over here, so specifically if it's starting at this specific address, let me search for this address, right? If you notice over here, so this is the address that I searched for. So basically this is the start of the main function, okay, and these two files I've highlighted that specific line. So this is the start of the main function. The right side is it's the non-script version, and left side is the script version. If you notice, in the script version, it basically strips off all the symbols from your executable, right? This main symbol, your debugging information, and then all the other. So this dummy function, it starts at 49D45. Okay, so all this symbol, you sort of like don't know where your function starts, where your function ends. So all that information is sort of stripped away from your executable, right? So this is what usually, like, it means whether it's a script binary or a non-script binary. Okay, so why this is important is because in most of real world applications, right, you won't be having a non-script binary. uh, you will be having a script binary where you won't sort of have any clue of where your function starts or where your function ends. So basically, if you look at this file, the non-script version, you can sort of identify, okay, this is my main function, execution starts over here, it calls a function dummy, okay, and so you sort of know how your control flows through just by looking at the object dump. But over here, you won't know where your execution will start, where it will flow through, unless you sort of keenly look into each instruction and sort of figure out what it does. You won't be able to easily figure out what your application will, the logic of your application, right? And usually, all the programs that are deployed will sort of strip all the symbols to make it harder for any um uh, attacker or someone to find an exploit, right? This just like extra difficulty, but there are tools which sort of try to analyze the binary and give useful names. So that's sort of like advanced tools, but this is generally the difference between script and non-script binaries. Okay, and another thing that I wanted to show is the file size of a no, dynamically linked application, right? So if I remove this thing, and if I see the file size, okay, of a.out. So for a statically linked, it was 700 KB, but for a dynamically linked, if you see, it is 16 KB only, because that glibc, right, that source code fully, it amounts to around like 600 KB. Okay, so all that source code is sort of linked as part of your code section when it is statically linked. It is having like a separate copy on your physical memory. It is stored on the disk, right? This file, everything. So a statically linked application will be having like 10 times, or how many times? 10, 60 times, right? 60 times increase in size for a statically linked application. But whereas in dynamically linked, you are not copying all the code into your executable, into your binary. Instead, you are just having a small logic where it calls the interpreter, and the interpreter sort of finds out where it is that shared copy is located in your memory. And the size of this dynamically linked application is 16 KB only, compared to 700 KB of that statically linked binary size, right? So this is what are the different stages of from a program to a binary, and how it gets linked, static or dynamic linking, and the different ways it gets linked, and whether it's like stripped binary or non-stripped binary, and what it means when we look at the file type of a dynamically linked application, this interpreter, and all that stuff. So we had a brief overview of uh, dynamically linked application and statically linked application, right? So with this, we sort of finish the entire pipeline, as in program to binary. Uh, we have looked in detail all the different stages, the pipeline stages, when we want to convert a program into a binary. Okay, and so that's it for today's lecture. We will wrap it up. It's 8:40 now, right? In tomorrow's lecture, we'll sort of start looking into assembly instructions, and we will look into how the stack gets controlled, how your stack, how does the stack gets manipulated at runtime, and all those stuff, and also a bit of assembly refresher, like various instructions that are present in x86, ISA, and all those stuff. We will just have a brief look and go into the details of how the stack is maintained at runtime, why do we need the stack, and all those things, right? So those we will look into in tomorrow's lecture. So any doubts in today's lecture or the previous lecture? So someone has asked a doubt, what's the difference between 32 and 64 bit. So basically 64 or 32 bit means it depends on your register size. Okay, so we'll discuss all these registers tomorrow. So basically, the any load, any data you want to access as part of your instruction. Say I want to add two numbers, right? What's the size of those two numbers, maximum size? If it's a 64-bit number, it means 64-bit architecture, right? If it's like 32-bit numbers only you can add, means it basically means you're having a 32-bit architecture. Like the maximum size of a number or something you basically can add in a single attempt, like that instruction supports. You can add a higher digit number, you will have like extra routines or some specific software, but basically 64-bit or 32-bit denotes the size of the registers or that word size of that processor they mentioned. Okay, so any doubts in today's lecture, static linking and dynamic linking? Any specific queries? Okay, if not, then we will wrap up the session. Thank you all for attending the session. Let's meet tomorrow. I will share the resource. So resources, the slides and videos, right? So I have posted on the Discord channel pertaining to that specific week. Okay. So if no other query are there, we can end the session. Thank you all. See you tomorrow. Thanks, Nirmal. Thanks, Artishri.